Kia ora and welcome to this video on question 5 of the 2021 Scholl Calc exam. There's 4 parts, 3 of them are complex numbers related, and given it's a question 5, the problems tend to be a little bit harder than earlier questions in the paper. However, there are a couple of nice ones in this one. 5b in particular is a really nice question, however it's got a step in there that is easy to get wrong. Question 5c is actually quite a quick question, but if you go down the wrong path, then good luck. And 5d I think is probably the hardest question in the exam. Again, quite easy to think you've answered it correctly, but in fact you haven't, and we'll talk about that detail soon. Okay, 5a. Consider the points 1, 2 and 3, 4. BC is a line perpendicular to the line AB. So we'll start off with that. Let's get the picture roughly to scale. Okay, we'll go 1, 2, about there. And 3, 4, about there. That's point A, that's point B. And we're told that BC is a line perpendicular to the line AB. So if I draw that line AB through there, BC must go through B. It's perpendicular. And we're told the length of BC is equal to, well, if you didn't know that, the absolute value symbols around a line means the length of it is equal to 4 times the length of AB. Okay, so we know what the length of AB is because it's just the distance between 2 points. We can use Pythagoras to find that. Got 2 in this direction and 2 in that direction. 2 squared plus 2 squared is 8, so AB is equal to root 8. And BC therefore is going to be 4 root 8. So we need to go 4 root 8 in this direction here and 4 root 8 in that direction there. Perpendicular tells us something about the slope. Okay, the line AB has m equals 1, so BC must have therefore m equals -1. Got my therefore symbol in the wrong place, it kind of reads a bit weird. Therefore BC m equals -1. Now we could do this algebraically, and we could call the points C, saying find the possible coordinates of C. We could call them x, y, and then set up an equation. But if the length is 4 times longer, if the hypotenuse is 4 times longer, and we've got similar triangles appearing here because the angles are the same, then we just need to go out 4 times the x direction and 4 times the y direction. So from B, we either go out 8 and down 8, or we go up 8 and back 8. Okay, and that will be enough to solving the problem. It's 4 times 2, because it's 4 times the hypotenuse, it must be 4 times the adjacent and the opposite side. Okay, so C, if I start with the B coordinate, x coordinate of 3, and add 8 to it, I get 11. If I start with the y coordinate of 4, and I subtract 8, I get -4. Or I start with the x value 3 and take away 8, get -5. Clearly my diagram started off to scale and is no longer there. And I take the y value of 4 and add 8 to it, and I get 12. Okay, so those are the 2 answers to the problem. And I didn't have to do any difficult algebra to get that. Okay, part B. If z equals x plus iy, where x and y are real, find all complex numbers to the complex solutions to the equation. So z plus 1 over z bar equals z bar plus 1 over z. Now there's a quick way to solving this problem actually. So I'll do that, and then also, like, if you didn't notice it, there's another way. You could put these fractions together and you'd get z times z bar plus 1 all over z bar equals z z bar plus 1 all over z. Okay, it's just putting the left fractions together, the right fractions together, and notice that the numerators are the same, so therefore the denominators must be the same. So therefore z must equal z bar. And for a complex number to equal its conjugate, the imaginary part must be 0. So if we're talking x plus iy equals x minus iy, that's only true if x equals x and y equals 0. So x is any real number, and y equals 0. And there's a catch to it, because if we make y 0 and x 0, we've got a 1 over z in the question, and 1 over 0 is undefined. So x is any real number except 0, and y equals 0. In other words, for this equation to be satisfied, the complex solutions must be purely real. The solutions are purely real. If you didn't notice that putting the fractions together sort of thing, if we just sub in x plus iy and do this in a standard way, x plus iy plus 1 over x minus iy equals x minus iy plus 1 over x plus iy. Okay, and then we times, we get these fraction ones to be complex numbers in standard form by timesing by the conjugate. So I've got x plus iy plus 1 over x minus iy times what am I timesing by? X plus iy over x plus iy equals x minus iy. This is a bit tedious given that the problem was quite quick to solve. X minus iy over x minus iy. Well, we've got an x on both sides, we can cancel those to start. Iy plus x plus iy all over, when we times a complex number by its conjugate, we get the real part squared and the imaginary part squared, equals minus iy plus x minus iy over x squared plus y squared. Now, I can break those fractions up into imaginary parts and real parts. And the reason I'm doing that is because I've seen that they've both got the same real part. So I can cancel off that and cancel off that. What do I want to do from there? I can divide everything through by I. Every term's got an I in it. So divide by I, divide by I, divide by I, divide by I. I can times the whole thing through by x squared plus y squared. So that will be y times x squared plus y squared plus y equals negative y minus, negative y times x squared plus y squared minus y. Okay, and this, I can divide everything through by y. I've made a mistake there. I'm just going to keep going and we'll talk about it, because I said at the start of this video I would show you how you can easily make a mistake in this problem. And then we end up getting 2x squared plus 2y squared equals negative 2, or x squared plus y squared equals negative 1. Now remember that x and y were real, So this seems like a contradiction. How can you take a real number and square it and an imaginary number and square it and get an answer that's negative? So it'd be easy to say here there are no solutions. But I lost the solution at this step. Think about how I did that. I divided through by y, and y could have been 0. If y was 0 on all of those terms, I would have got a true statement. So at this point I needed to recognize y equals 0 as a solution. Z equals x plus iy becomes z equals x if y is 0. And so the complex solutions are real numbers, again provided if x doesn't equal 0. And it's important to note there that complex numbers include real numbers, they include purely imaginary numbers, and they include complex numbers with a real and an imaginary part. So complex numbers is the overarching set of numbers, the real numbers is just a subset of them. So the question didn't have to say find the real solutions to it. We've found complex solutions that just so happen to be purely real. But that method there was a lot, it was like a standard level 3 excellence question in terms of subbing an x plus iy, but it was a lot more tedious than the first method. Okay, part C, we don't want to sub x plus iy into this. If you do, you go through screeds of algebra only to get to something you can't interpret at the end. The question says that we need to sketch the locus of points, so we really need to understand what this equation is telling us in the Argonne diagram. So we've got z minus 2 plus 4i, the modulus of it, plus the modulus of this is equal to 4. Okay, if you weren't aware of this already, the way that we read something like this, I don't know, z minus z1 is the distance between z and z1. So provided that there's a minus in the middle of it, when we've got the modulus of a difference between two complex numbers, it is actually the distance between z and z1. And easy to explain that, if I took, in the Argonne diagram, suppose I took a complex number here, z, and I took away z1. Let's make z1 equal to 2 plus 4i. If I took away 2 plus 4i from this complex number z, I'm going to take away 2 off the real part, and I'm going to take away 4 off the imaginary part. So I'm going to take away 2. That will move me to the left. That distance is 2. I'm going to take away 4i as well. It's going to take me down by 4. And that there will be my z take away 2 plus 4i. And the modulus of that, well, 2 plus 4i, if I look at this distance here, the modulus, this length here is the modulus of z minus 2 plus 4i. It's the distance of that complex number from the origin. It's going to be the same as the distance between z and 2 plus 4i, because this will be 2 and this will be 4. Okay, so this is like a parallelogram there. Whenever you see the difference of two complex numbers with a modulus around it, you need to remember it's the distance between those complex numbers. And if you do that, the next hurdle is to realize that this is an ellipse. The locus is an ellipse with foci at 2 plus 4i and 3 plus 6i. And the reason for that is we've got the sum of two distances is equal to a constant, and when you have an ellipse with foci, the sum of the distances between the ellipse and the foci is always the same. No matter where abouts in the ellipse you draw it, you get the distance from one foci to the ellipse is plus the distance to the other foci is a constant. Okay, so we can graph this. Again, I'll try and set out to make this to scale. And go 2 plus 4i is our first foci. And 3 plus 6i is our next one. And we get an ellipse that is around that point. That's a terrible start. Let's try and get it a bit better. Yeah, that will do. And the last thing is to say, well, where does that 4 come in? And it turns out that the 4 there is always equal to 2a where a actually no, let's say that a is from the center out to the vertice. So that's a. In other words, 2a is the diameter of the longest axis of the ellipse. So if you're a little bit rusty on your conics and stuff, it might pay to look up the definition of an ellipse and what a, b, and c stand for. Normally we have an equation that's x squared over a squared plus y squared over b squared equals 1, where a and b are the radius in the x and the y direction, sometimes called the semi-minor axes. And then we've got another equation that connects these things together. It says b squared plus c squared equals a squared, which looks like Pythagoras, where the foci are at c0 and negative c0. Okay, so that's a little bit of extra stuff that you'd need to know to deal with ellipse problems. But in this particular question, what you need to realize is that that there is the locus, and I've drawn it terribly because the other thing to realize, actually I'm going to get my ellipse in a slightly better position so that you can see this. The diameter of that ellipse, actually, if I extended that line, it would go through the origin. The 2 points 2, 4 and 3, 6 are collinear with the origin. It did ask to sketch it, so in terms of the size of the ellipse, it turns out that the ellipse is actually only in the first quadrant. It never breaches the axes. One way to work that out is to make, instead of go z equals x plus iy, make y a variable and let x equals 0. So for example, if I had this equation, z minus 2 plus 4i plus z minus 3 plus 6i equals 4, and I said, okay, let z equal x plus iy, would give me any complex number that satisfies the equation. So z is somewhere on the ellipse. But if I said, okay, what about purely imaginary numbers? Are there any? Does this ellipse cut the y-axis? So I could say, what about x equals 0, and just go and work out iy as the solution. So I'd go iy minus 2 plus 4i plus iy minus 3 plus 6i equals 4, and I'd do my standard complex number stuff to try and find solutions for y, and you'll find that there aren't any real solutions for y, so the ellipse can't cut the y-axis. Okay, we don't need to do that for this problem, but just a sketch in the first quadrant would be enough. And then the second part of the question says find the maximum value of the modulus of z. So the modulus of z is the distance that z is from the origin. So if z is, say, this point on the ellipse, then that there would be the modulus of z. And the biggest value of that is, of course, going to be if z is over here, because the furthest from the origin will mean the biggest modulus of it. And it just so happens, because this diameter is collinear with the origin, we just need to find the length, the distance from the origin to that complex number. we don't need to find that complex number. It says find the maximum value of this modulus. Okay, so the diameter is equal to 2a, and we already know the center of the center here is 2.5 in the x direction and it's 5 in the y direction. So we can find the distance of that point from the origin, and then we can add 2 to it, because in this question it's the sum of the distances is equal to 4, means that 2a is equal to 4, which means a is equal to 2. So the max value of the modulus is equal to the distance from the origin to the center plus the extra 2 to get to the far side of the ellipse. And if you evaluate that, it's 7.590 to 4 sig fig. It does have an exact form, but it's not that nice, so evaluating as a decimal seems all good. Okay, that's quite a tricky question if you don't have the basics of the geometry of the locus questions. So other ones that you should be familiar with is if you had something like z minus a complex number is equal to, say, a constant k, that would be a circle centered at z1, radius equals k, where you might have something like z minus z1 equals z minus z2, and that's a perpendicular bisector between z1 and z2. So that says the distance between z and z1 is the same as the distance between z and z2. So it'd be a perpendicular bisector. Now those things are stuff that you could brush up on in your level 3 that will help you with recognizing a scholarship problem without doing any x plus iy substitutions. Okay, question D, the hardest question in this exam in my opinion, involves an isosceles triangle with two angles that are equal to alpha, vertices A, B and C represented by complex numbers z1, z2 and z3, and we need to prove this result. The first thing to notice is that when you've got this left hand side here, z2 minus z1 is a complex number because z2 and z1 are complex numbers. So we could be like, okay, z2 minus z1 is equal to some complex number r cis theta. And the question is, like, and the reason I'm doing polar form is because there's angles and geometry involved, but the question is, where does the r and the theta relate to the diagram? So using our knowledge from part C, the modulus of z2 minus z1 is equal to r, and that's also the distance between z2 and z1. So we can write that there, r on the diagram, and the argument of z2 minus z1 is equal to theta. And where does that appear on the diagram? What you need to know from that is if you take a complex number z2 and you take away z1 from it, well, z1 is here. Complex numbers are always relative to the origin. If you take away z1 from z2, we end up here, and there's a parallelogram there, and this here would be z2 minus z1, this here would be the argument, and it turns out that that angle is the same as this angle. So that angle there is theta, where the line I've drawn is parallel to the real axis. So I just get rid of all this extra annotation that I don't need. When you have a complex number z2 minus z1, you start at z1 and you say, what angle do I need to move in anti-clockwise to get to Z2? So the second one here is the starting point, and this is the finish. So that angle theta is now shown on the diagram. Likewise, we can do the same thing for Z1 minus Z3, which is the second part of the left-hand side. Or Z1 minus Z3, the modulus of it is this distance here, which turns out to be the same. The modulus of Z1 minus Z3 is the distance between Z1 and Z3. Because it's an isosceles triangle, it's also equal to R. And the argument, we start at Z3 and we say, what angle do we need to move to get to Z1? So that there, I'm going to call that beta. So Z1 minus Z3 is R cis beta. Okay, so that's my left-hand side setup. Go working in polar form. I would need to copy that diagram out into my answer booklet because I keep the question booklet. When you sit the exam, you would keep the question booklet. So I've got left-hand side is equal to Z2 minus Z1 times Z1 minus Z3, which is equal to R cis theta times R cis beta, which equals R squared cis theta plus beta when we multiply complex numbers in polar form. And the reason I chose polar form was initially because there's geometry involved, but it also makes multiplication quite simple. You just multiply the modulus of each of them and you add the angles. Okay, now let's look at the right hand side. The right hand side brings in alpha, and it's also got Z2 minus Z3 in there. So I just move this out of the way. Okay, what have we got on the right hand side? We've got half squared. Okay, we're squaring all the stuff here. We've still got a complex number in there. A half is a number, sec alpha is a constant as well, but Z2 minus Z3 is a complex number. So we've got a half squared, a quarter. We've got sec alpha squared, which is sec squared alpha, and then we've got Z2 minus Z3 all squared. So Z2 minus Z3, so this is a complex number too. Also, what is its modulus? Look at the modulus of this. Let's look at the modulus of Z2 minus Z3. It's the distance between Z2 and Z3, which is actually, if we split this, because it's an isosceles triangle, make it into two right angle triangles, we can use trigonometry. This length here is R cos alpha. So the distance between Z2 and Z3 is equal to 2R cos alpha. And the argument of Z2 minus Z3, what is that? We start at Z3 and we head in the direction of Z2. Well, we've already got that on the diagram. That's alpha and beta added together. Alpha plus beta. Okay, so my right hand side of this expression, which equals a quarter sec squared alpha times Z2 minus Z3 all squared. I know that complex number Z2 minus Z3, I can write it in polar form. As its modulus is 2R cos alpha, cis, its angle is alpha plus beta, and we need to square that. When you're squaring, you're timesing by itself, so you square the modulus and you double the angle. So we get 2R cos alpha times itself, which is 4R squared cos squared alpha, and then cis, double the angle, 2 alpha plus 2 beta. Okay, and we can see there that a quarter cancels with a 4, and sec squared cancels with a cos squared because they're reciprocals of one another, and we get r squared cis 2 alpha plus 2 beta, which looks almost correct. Okay, the left hand side there was this, the right hand side was this, so we've got the r squared in both of them, and we just need to prove that those angles are the same, theta plus beta and 2 alpha plus 2 beta. So let's go back to the diagram. How do we prove this? It's still a little bit of year 11 geometry. This angle in here is 180 minus 2 alpha, and this angle in here is 180 minus beta, because co-interior angles on parallel lines add to 180. So I've got all of those angles, 180 minus 2 alpha plus theta plus 180 minus beta, must add to 360, angles around a point. 360 cancels from both sides, and I've got, where am I trying to prove? 2 alpha plus 2 beta is theta plus beta. Okay, so if I move the minus 2 alpha and the minus beta to the other side, I've got theta equals 2 alpha plus beta. I need an extra beta in there, so theta plus beta is 2 alpha plus 2 beta, and there it is. Theta plus beta equals 2 alpha plus 2 beta. Left hand side equals right hand side, because theta plus beta equals 2 alpha plus 2 beta as per my diagram, which I said you'd need to include in your answer. Therefore the proof is complete. So the proof had two parts to it. The left hand side and the right hand side, we had to prove that the modulus was equal. We also had to prove that the argument of each complex number was the same. Quite a tricky question, but probably the problem that determined who got top scholar in that year, because it's right at the end of the paper. I'd say don't do question 5D first. It's usually one of the last ones to do because it's the hardest. Alright, catch you in the next video.